one classification what for the switches that we have is this classification that you see here into unidirectional and bidirectional. So unidirectional here and bidirectional on the next page. Okay. So can conduct or interrupt current only in one direction, right? And then you have unipolar and bipolar. Unipolar has a small reverse breakdown voltage, so you should not really bias the switch in the reverse direction with any large voltage. It cannot tolerate that voltage. This type of switch is called unipolar. But bipolar switches can stand large reverse voltage. So typically what we do, it's very common, almost all converters they do. You have a unidirectional unipolar switch like this one. It can only conduct the current on this direction. And then you have a diode connected in reverse direction. So this makes sure that this switch is never biased in the reverse direction as at a large voltage. So and then this circuit symbol we use, we call it switch cell. Whenever we use this circuit symbol, it basically shows that you have a switch here that can conduct or interrupt the current in this direction. And then there is a reverse connected diode. So if need be, the current can flow back in this direction through the diode. So you can say it's bidirectional, but the reverse direction is done through the diode, not through the switch. So it's very common. And you will see when we get into the converters later today or tomorrow, you will see how this arrangement will work very nicely. So bidirectional switches, we would wish to have them, but technology is not really there. There are some types of technology to actually have bidirectional switches, but it's not very efficient and very mature. So it's safe to say that we really don't use bidirectional as a single entity, right? We do not have a technology for that. Okay, so types of power converters. Basically, if you look at here, I mentioned 4, and it's based on whether it's DC on one side or on the other side or AC. So DC converters or DC to DC converter or DC-DC converters. Basically, both sides of the converter are DC. So we use the converter to either increase the voltage level or decrease the voltage level. So it's buck converter for when you want to decrease it, or when you increase it, it's boost converter. And some applications you may want to have both types together. So we can have buck boost converters. Okay. A DC converter, or in some applications, even you may not be focused really on increasing or decreasing, but you may want to use this converter for other purposes. For instance, if you want to isolate one side from the other side, you can use it. Use a converter. Again, you will see later how to do that. So from that perspective, some of these DC-DC converters also they give you isolation. Some of them they do not give you isolations. So especially in the context of DC-DC converters, we have isolated and non-isolated converters, which this terminology is very, very much used. So isolated and non-isolated. By isolation, we mean galvanic isolation between two sides. We have rectifiers, AC to DC, converting AC to DC, as the name indicates. And AC could be single phase or 3-phase. Okay, so the power flow is from AC to DC in this one. And that's why it's called rectifier. Inverter is the other other extreme of this one. So it's DC to AC. The power flow is from DC to AC. On the AC side, it could be single phase or three phase. And then AC or AC to AC converter, the name indicates it could be single phase or three phase, or even one side single phase, one side three phase. Applications of power electronics. Again, I tried to classify them in, I think, 4 different groups. One is power quality applications, and then one is power system applications, one is distributed energy applications, and motor drives, we'll see. So power quality, there are a few different applications. One of them is active power filter. And if you look at this diagram here, it explains what active power filter does. It's basically when you have a load connected to the power grid, and that load is nonlinear load. A lot of loads that we have are nonlinear load. And load is nonlinear when the current that absorbs from the power grid is not sinusoidal. So this current is not sinusoidal, it's distorted. For that reason, this power grid does not like that current, because distortions or harmonics have multiple impacts on the power grid. So especially if the load is large, like industrial loads, there are, codes and standards by the power grid that would not allow that to happen. So active power filter here is a converter, power electronic converter, that what it does, it generates the harmonics that the load needs locally. So therefore, this current remains sinusoidal. And a static compensator, or a StatCom, is very similar in terms of operation to active power filter, so the same concept here, but it's basically used for reactive power. So reactive power is also something that we don't like in many applications. Again, it is especially if it's a large load, industrial load. So if you can provide that reactive power locally using a converter here, which is called a static compensator, then this current remains only active current, not reactive current. Dynamic voltage restorer is similar again, but now it says, now this load is very sensitive, let's say, and this power supply here can have voltage fluctuations. So you want to make sure that the voltage that this load receives is very reliable and very smooth, and the fluctuations of this voltage, or even outages if you want, short temporary outages of this voltage, will not go to the load. So what this DVR does, dynamic voltage restorer, it makes sure that always there is a voltage generated at the output here, such that this voltage plus this voltage, which is the voltage across the load, is always reliable and secure. So this, one of them you can say it's series, the other one is parallel, you see, and now you can combine them together like this. So you have unified power quality conditioner. So if you combine them together, and now you can address a lot of problems on both sides in terms of harmonics, in terms of voltage quality, in terms of reactive power, and so on. In power system, this is one of the main applications of power electronics, flexible AC transmission systems or FACTS devices. So this is a transmission, as the name indicates, transmission device, which is placed in the transmission line. And the objective of that device is to control and increase the power flow from one terminal to the other terminal, from one side to the other side. And the way it works, basically, if you look at the voltages here, let's say VR for receiving and VS for sending. So VR and VS sinusoidal. This is the phasor diagram of this. And the angle between them is delta here. So this is the power angle that determines how much power is transferred. This real power is this one here. This equation for real power. So now if you inject a small voltage here, obviously this voltage you cannot inject too large because already this is transmission system. So the voltages are thousands of volts or tens or hundreds thousands of volts. So you can inject a small voltage using this power electronic converter. That is this voltage here, VC. And this is the voltage drop across the line, right? So by controlling this VC, you can control the tip of this vector. And then you can control this delta. Right. And also reactive power, but mainly the real power you can do. HVDC systems, high voltage DC transmission systems. Basically, with the advancements of power electronics, now we are looking at this large transmission line, which is DC, not AC. Because we said we are not very, we have a lot of challenges with AC transmission. First of all, we talked about power losses, which still will be here, even though will be less compared to the AC. But then, if it's DC, we don't have reactive power, right, in the DC system. And also in terms of synchronization and stability is more, I would say, stable than AC. So all these advantages, a lot of people have been researching, and even some practical deployment of these systems are there. I don't know about India, but I know China have been using this technology very much. Some of the European countries also as well. So here you have one AC-DC, and then again another one, converter. So two converters. And even these two systems can be completely two different AC systems. One of them, let's say 50 hertz, 60 hertz, or even two completely separate AC systems. They don't have to be synchronized anymore. So by controlling these two converters, you can control the power flow between these two. Okay. And now rectifiers and motor drive applications. So here is the case that you have an AC or DC power supply already, and then in the case of rectifiers it's AC, and then you have some DC loads that are connected to this AC power system. Motor drives, if it's a DC motor, it will be exactly the same thing here. So if you want to control a DC motor connected to an AC power supply, you have basically a rectifier. Motor drives, basically it's another name for the same concept. Motor drives, all of them are converters, but are used specifically for the controlling the operation of a motor in terms of either speed or angle, right? So it's called, in this context, it's called motor drive. Okay. And then we have DC motor drives, AC motor drives, and AC motors are majority are induction machines, but some of them synchronous machines as well. And then lastly, backup supply and distributed generation applications. So these are, again, you can merge them together in one application. Uninterruptible power supplies, UPS, these are devices that have a battery that store energy, and they are located close to some sensitive loads that you don't want to, for those sensitive loads to lose power when the main utility lines are not available for some extended amount of time. DVR, we said, it can only tolerate for short amount of time, but this is even for an extended amount of time. Okay. And distributed energy storage, right? It's a battery that can store energy and release energy. Electric vehicles, you can say this is one particular specific type of the distributed energy storage that stores energy. Microturbines, we said these are basically generators that generate based on normally natural gas, but they generate high frequency AC, very high frequency AC. And for that reason, these are compact devices that can tolerate or that can generate larger amount of energy at a smaller size, at a given larger frequency, 1 kilohertz to 2 kilohertz frequency. So you can convert that to 60 hertz or 50 hertz and connect to the power supply using converters. Wind turbines, they generate AC, but that AC is not very stable and in terms of frequency and magnitude. And so you cannot directly connect wind turbine to the power grid. So again, you need converter to convert that to a stable AC power. And then solar photovoltaics, they generate DC power. And these are basically the only one that directly generate DC, right? And then you need to, if you want to connect to the AC power grid, you need to have an inverter to convert that to AC. Okay. So that basically is a summary of this chapter. So I need to open the other file. I think I need to open with the other browser. Let's see. Need to open with the other one. Yeah. This one. All right. There you go. Thank you. Okay. So this chapter is about converters. So going into details of, I think, 4 or 5 different converters and trying to understand how they work, and analyze them and model them, so to speak, mathematically. So the simplest one that almost every standard course in power electronics starts with is this one. This is called standard buck converter. So you have one side, again, let's go with side A and side B. So you have side A here, side B, and there is a switch here, there is a diode here, and there is an inductor here. That resistor is not a physical resistor, it's basically a model of the resistors that you have in the circuit, in the inductor or in the conducting mode of the switch, or in the cables. So if you look at this transistor or this switch here, the power can flow in this direction. It cannot go back. So the power flow is from this side A to side B, right? So the way it works is, let's assume that you turn on this switch. So this terminal now is connected to this terminal point here, right? And then let's assume, so this voltage, which is VA, now here across this diode, is larger than this voltage VB. So a current will flow in this direction. This is inductor. So a positive voltage is across the inductor. Its voltage starts increasing up, right? So let's say this voltage is VA and this voltage is VB. So VA minus VB, and it's positive. So this is V inductor. When it's positive, the current will start going up. So this current will start rising. This is IL, or I, basically. If you just keep it like that, this current keep increasing, 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 and will damage the inductor, right? But at some point, you turn off the switch. When you turn off the switch, now this current flowing into the inductor has to be continuous, and it has to find one path for it, right? So you block this path, it will continue through this diode, right? So now you will have this loop here closed. Before you had this one, now you have this one. Right? So this voltage becomes 0, and this is VB. So the voltage across inductor becomes 0 minus VB. And if VB is positive, that becomes negative. So the current will go down. So here, let's say you go to negative VB, and let's say this is negative. So the current will go down. So now you have a stable situation. The current can go up and can go down. You can control it, right? So for that reason, VA should be larger than VB. And this should be positive, right? So that's why it's called buck converter. So this voltage has to be larger than this voltage in order to operate. Okay. So really I explained almost everything here, but if you go details of that, first of all, in order to facilitate the control and modeling and analysis, we need to introduce this concept, which is concept of switching function, mathematical representation of how we turn on and off the switch. Let's define this mathematical function equal to 1 when you command the switch to become on. In other words, when you apply the required voltage to the gate of that switch that you expect the switch to be on. And then 0 otherwise, when you apply the negative voltage or the voltage needed to turn the switch off. Okay, now I'm going to talk about pulse width modulation. Again, I'm sure most of you know that, but pulse width modulation is one technique to generate this switching function in practice. Because we always, in engineering, we want to find techniques and ways to generate things or to operate things in the best way. So the way that it works, basically, it has a signal here, we call it carrier waveform. So it's like typically a triangular waveform with high frequency like that. And then we have a low frequency signal modulation waveform. So let's say this one. So low frequency. So you compare this one and this one, you subtract them or you compare them. And depending on whether this is larger than this one or this is smaller than this one, you output 1 or 0, right? So here, for instance, M is smaller than C in this region. In this region, M is smaller than C. In the other region here, M is larger than C. So here you have 1, and here you have 0. 0. Right. So that gives you a switching function, either 1 or 0, depending on whether m is larger than c or otherwise. So this technique is called pulse width modulation. So for instance, in the context of this buck converter that we just discussed, let's say m is a constant, right? And this is carrier waveform between 0 and 1. And then when m is again larger than c, you have 1, and then you have 0 here. So this is the voltage across the diode, which is either 0 or VA. And this is the voltage across the inductor, which I said is VA minus VB or negative VB. Right? We discussed that. So negative VB. And if VA minus VB is positive, the current will go up and the current will go down. During this time, the current flows into the switch. During this time, the current flows into the diode. So this shows a stable scenario. Now, if you increase m, right? If you increase m, you increase the time that switch is on, and you decrease the time that the switch is off. So the current, the time that the current is rising becomes larger, and the time that the current is falling becomes smaller. So you increase the current that goes to the inductor. If you decrease m, you decrease the current. So you see this is a very fine point, control point, m of t, that by increasing it, you can increase the current. By decreasing it, you can decrease the current. That's basically the beautiful thing about PWM, that we like it and we use it. Okay. The relative time that the switch is on, let's say the entire time is called switching period or switching cycle. And reverse of that, which shows number of times that you turn on the switch on and off in 1 second, is called switching frequency, which is basically the frequency of this carrier waveform. Right? So frequency of this triangular waveform tells you how much is your switching frequency. The ratio of this time to the entire time is called duty. It's called duty cycle, yeah, D. So TS is used for sampling time. Okay. Now, in terms of equations, you can immediately see that now this switching function I told you is very, very practical and very useful to model these power electronic devices. So the voltage across the diode, let me go back, it's worth it one more time to that diagram. Where was it? Here, okay. So this is the voltage, you can say at the out terminals, sorry, the terminals of the so this is filter. So you can say, either you can say your converter is this one, or include the filter. Some people include the filter inside the converter, some people not. But anyway, if you do not include the filter in the converter, these are the voltage that the converter generates at this point, VT. And it's equal to VA or 0. When the switch is on, is equal to VA, and the switch is off is 0. So you can say V is VA into S of T, switching function, mathematically. Right. Now that you have this voltage and you have this voltage, you can say this voltage minus this voltage is equal to the voltage across this one. So these two equations really summarize the mathematical model of this converter. These two. So the first equation here and the second equation here. So that's the one I just said, and this is the voltage equation in that loop. So the voltage drop across the inductor, LD over dTi plus Ri equal V minus Vb. Okay. Now, we also, here we have only one switch, so I'm using S1. We shortly will move to a case we have 2 switches or 4 switches or 6 switches. So for that reason, I would like to keep that S1, and then we'll have S2, S3, S4. And then for each switch, we also define the negative or the NOT of that switch, S1N for NOT, which is 1 minus S1. So when S1 is 1, S1N is 0. And when S1 is 0, that is 1. So it's the complement of that switch. So if you look at that equations, those two equations that I just explained, and this definition of S1 and S1N that we have here, you can say when the switch is on, the current is I, and it's flowing into this inductor. And the voltage on this side is VA into S1, and this point is 0 voltage, and this is VB. And then when the switch is off, the current flows into the diode. So the same current I flows into the diode, and the diode is S1N. So when the switch is off, the diode is on, and vice versa. So this switch and this diode is always opposite of each other. So if you look at this, everything is mathematical. This is a current source. This is another current source. This is a voltage source. And these are two resistors and inductor. And then you have voltage here, another voltage here. So this perfectly models how this converter works. In other words, if you know VA, if you know VB, and if you know S1, and obviously R and L, you can simulate this in any software that you have. And the result of this simulation tells you what this converter will do in terms of current, how much current this converter generates. Right? So if you want to simulate it, and there is no assumption here, we made no assumption, so this is a completely accurate model. It's called switching model. It has no approximation or no simplification. However, we like to use a more simplified model because normally for the control or operating scale, we are not interested in all these switches. These switches, keep in mind, are happening at very fast rate, tens of kilohertz, or even, like I said, in GIAN switches, hundreds of thousands of times per second. So you don't want really to engage yourself in those very short time, unless your research is particularly in that aspect, okay? But if your research is in control or power system operation of the converter, you're not interested in what's happening in that time scale, right? But if you are a power electronic person researching on the power electronic side of the switches, you may want to go into details and work with this model, right? A lot of software tools that we have nowadays, like PSIM, PlexSim, those kind of software really use these switching models. So they can simulate this for you perfectly, then give you all the details for this one, but they are very slow, right? They take a long time to simulate. So can we derive a model that represents this system but avoids those very short time scales? In other words, tells us how much current on average is generated not in the scale of cycles, not in the scale of intercycles. So that is the concept of average model or control model that I'm going to explain. And you see, this is the model that we need to learn and work with if we want to understand what the converter is doing in terms of interacting with other entities. Okay, So a little bit of mathematics, how this model is derived. It's basically the mathematics is based on Fourier series. Fourier series, you all know. This, it says if you have a periodic function, let's say voltage Vt, you can write it as a DC plus a combination of harmonics, right? And then the Fourier series tells you how to calculate AN, BN, B bar, all those things, right? These are the equations that you all know. So in our case, switching is happening, so the cycle period is one switching cycle, right? So this frequency, this omega s here, is the switching frequency in radian per second. So 10 kilohertz, 20 kilohertz, or even higher. When we say we don't want to engage ourselves in those short times, we say, forget about this. And only tell me what's happening here. Right? Tell me what's happening here on the scale of DC, what is happening. And that DC doesn't mean DC, it means slow compared to this one. So that is happening at 100 kilohertz. This is happening, even 60 hertz is DC compared to this one. Even 600 hertz is still DC. Remember, when we say DC in this context, it means that. So it's slow terms. Okay. So this is the mathematics that goes. So for every waveform, we can write it as a low frequency, or we can say DC term, and a high frequency term, according to this explanation of the Fourier series. Now, if you have that one, that thing, now you can break down the equation. And remember, VA and VB, these are the voltages that represent physical systems. These are DC again, right? These are coming from battery or power grid or solar panel or whatever. These are not high frequency. So those So VA and VB only are DC, low frequency, but current, the inductor current, and V across the diode has both components, both DC and AC. So now we can break down the equation into DC and AC. So that voltage equation. And the DC part, according to Fourier series, is the 1 over Ts integral of that waveform over one cycle, one switching cycle. And now that switching cycle, you just move it with time, right? So it looks like you are making average over every cycle. That's why it's called average model. So we say on every cycle what's happening on average. Okay, so the V bar is VA into S1. That equation is also valid. Right. S1 bar. S1 bar is the average of S1. Again, if you just picture that in your mind, what is the S1 switching function? Average of that is D, duty cycle, right? Because it's a waveform like this. It's 1 and then 0, and here is, from here to here is dTs, and again it's 1 here, so here is 1 minus d into Ts. So the average of this waveform is d, okay, duty cycle. Now, another interesting thing is that if you look at the PWM that we discussed, let's say from 0 to 1, and then your modulation signal, let's say here, M. And we said this is D. This is DTS, and this is 1 minus DTS. So you change M from 0 to 1, and duty cycle changes from 0 to 1. And it's linear. So the only option is D and M are equal. Right? Okay. The only function which is linear and converts 0 to 1 to 0 to 1 is equal, identity function. So we have this equation here. So the modulation index and the duty cycle in PWM is the same for buck converter, at least with this terminology that we used here. Or as long as you are using these ranges from 0 to 1, and then M, you define M just like that. Okay. So put all these together, and then you will see that now I have V bar equal VA into M. That's this voltage across the diode. And this voltage, V bar, minus VB is equal to LD over DTI plus RI. These are I bar, to be accurate. And if you take Laplace transform from these both sides of this equation, this becomes V bar minus VB, now in Laplace domain, equals LS plus R into I bar in Laplace domain. So M into VA, that gives you V bar minus VB, divided by LS plus R, that gives you I. So Laplace domain and Laplace the transfer function and those things we will discuss tomorrow. I don't think we'll start today. No, it'll be tomorrow. But just I'm giving some hint here for, I think most of you know, but for some of you, if you don't know, you will see it detailed tomorrow. Okay, so this model, for those people who work in control systems, they can connect to this model. It has a little transfer function here, one gain here, one subtraction. It's a very simple mathematical model that can be used very well for control purposes. And for that reason, it is also called control model. But it's nothing other than average model. So average model and control model, they are the same, but control model, I can say, is represented in terms of transfer functions or those things that we like. People in control like it. So you can call this control model. Also, another thing we can say about this model is, if you look, input to this model is M, modulation index, which is a control input. In other words, you can change it in your control circuit. That's the modulation signal to the input to the PWM. And the output of the model is the current. In other words, if you want to control the current of the converter using the PWM modulation index, this is a good model. So it is called current control model. If you want to control the current using PWM. Sometimes you want to control something else. I'm going to discuss that. But if you want to control the current, it's current control model. What are the other options? You may want to control the voltage. Which voltage? VA or VB? Again, both options you have. But one thing is, every time you work with a DC-DC converter, like and especially buck or boost, you can only control one thing, not more than that. So you can only control current or the voltage on A side or the voltage on B side. How can we derive the control models for those? So output, this is also very common. The other one, current control, is when you connect it to the grid. So you want to control the current flowing to the grid, or if it's bidirectional, to the grid or back to the converter. for instance, in a EV application, or if it's a solar panel application you want to feed. In this case, if there is no current, you want to control this voltage. Let's say you have a source here with a given voltage VA, and then you want to control the voltage here across your load, right? That's a very reasonable scenario. So in this case, again, without going too much into equations, you can see that this diagram is correct. Why not? M into VA generates this voltage here, average of that. This voltage minus VB, that's the voltage across this inductor. You divide it by the impedance of the inductor, that gives you the current flowing into this inductor here. So that I bar is this inductor. Average of that. For now, I keep the bar, I bar, but you will see as we go on, I drop that bar. So because now we all agree that we are focusing on the control side of the converter, not on the switching side of the converter. So that is the current flowing here. This current minus this current going, if there is something, this current goes somewhere else also. If you only have one load, that's it, this current is zero. But if this converter is connected to other net part of the network, there could be another current flowing here, right? So this current minus this current is the current flowing here, and then you multiply this current into this impedance, whether it's resistive impedance or otherwise, that gives you this voltage. So this current multiply this impedance, that gives you this voltage, and that voltage goes back here, feedback. So this is the control model for controlling this voltage. If you want to control the output voltage, this is the model that you have. The other option is if you want to control the input voltage. Let's say how you do that. I think, yeah, input voltage control. This is the diagram, it's in the next page. So here you want to control this voltage. For instance, this is the application, for instance, if you want to have a buck converter connected to, let's say, some solar panels here, PV panel. And then you want to control the voltage across the PV panel. Why do you want to control the voltage across the PV panel? Because by controlling the voltage across the PV panel, we will see tomorrow or the day after tomorrow, that you can control the amount of power that you can extract from the PV panel. Okay. So you put a capacitor here. You need that capacitor to have a voltage and then really have a support for that voltage to control it. And then the converter is here, the filter is here. Okay, so this case, the model is a little more complicated. See how it works. M into this voltage, VA, that you want to control. So M into this voltage that you want to control, that gives you the voltage across this dial. This voltage minus this voltage, which is now an external voltage. Remember, this is now internal, you want to control. This is an external voltage. So this voltage minus this voltage is the voltage across the inductor, divided by its impedance will be its current. Agree? Now, I have shown two models here, one based on power, one based on current. Both of them are correct. Let's look at the power, for instance. So now you have this current flowing here. If you multiply this current into this voltage, that will be the power which is given at this point, delivered at this point, right? The power at this point. Now, the power across this transistor and this diode, lost in this transistor and this diode, there are tiny amount of power. So you can just ignore that. So this power and this power are equal. This power and this power. Call it PC, right? So PA minus PC is the power going into this capacitor. And again, PA is coming from the PV. You can look at it as an external, minus PC is the power that goes into that capacitor. And we know the power of capacitor for capacitor, C into VC into VC dot is the power of capacitor. Voltage into current. Dot is for derivative, right? Is VC into IC. So this division here means that now the power of the capacitor at this point, this is power of capacitor, you divide it by VA or VC. VA and VC are the same. So you divide it by VA. And again divided by C, that becomes VC dot. Integrate that one, that becomes VC. Okay. So that is as far as power is concerned. For the current also you can to derive this equation. So once you have I bar, this current, and then you say I bar, that's the current flowing here, multiplied into M, I bar multiplied into M is the current flowing here. Because when the switch is on, this current is coming from here. So M or D represents switching function now. So when the switch is on, this current is equal to this one. So this multiplication basically says I bar into M is this current, IC. And now IC minus IA, this is current coming from the panel. Integrate that one, gives you the voltage of the capacitor. So unlike the other two models, this model is completely nonlinear model. And this really poses a challenge in terms of controlling the voltage. And then later on, you will see in the boost converter, we also have a situation. We normally don't use this model in the buck converter, but it's very common to use this in boost converter. Because boost converters are used for the first stage of the solar panels. Because normally we want to boost the voltage. Okay. So let me mention, I think it's a good thing. This is a nonlinear model. Why it is nonlinear? Because of these divisions and multiplications. Right? When you have division by a variable or multiplication into a variable, not a constant. If you have division by a constant or multiplication into a constant, that's fine. But when you have division by, you divide by a variable or you multiply two variables, that becomes nonlinear. Okay. Okay, one example here. As we go on and we go further and further into details, especially after maybe late tomorrow, we'll have a lot of examples, and most of them, they have simulations. So I will run the simulation files for you, and we'll try to practice a little bit of simulations. This one particularly, I don't think it has simulation. It's only calculation. So one example is about buck converter. It says, consider a buck converter where on the input side is a voltage source of 100 volts. Okay. And on the output side is a voltage source of 40 volts. It should be smaller. Okay, it's a smaller. The power rating of the converter is 10 kilowatts, so we expect to generate 10 kilowatt power. Switching frequency 4 kilohertz. Inductance is 400 microhenry. And total parasitic resistance is estimated at 10 milliohm. I told you this resistance is, we call it parasitic resistance, and it models a few things together. Inductor resistance, series resistance of the inductor. It's also cables, and it's also the on-state resistance of the switch and the diode. So for that reason, this is a parameter which is hard to really estimate. But it should be small, because if it's large, it will be a lot of power loss, right? It should be very small. So in this circuit, it's 10 milliohm. Okay, so find the duty cycle D at no load condition. When you want to have no load. When you want to have no load, in other words, no current, no flow of current. No flow of current means and this switch is here. And remember, this is 40 volts. And this is 100 volts. So if you want to have no flow of current, you should generate 40 volts here. If you generate 40 volts here across the diode, there will be no current flowing. Okay? So if you want to have 40 volts, V bar is equal to 40. Then V bar, what was the equation? V bar is D into VA. So D is V bar divided by VA. 40 divided by 100. 0.4. Okay. Compute the duty cycle D at full load condition. A full load condition means full load is 10 kilowatt. 10 kilowatt here. So at 10 kilowatt, you have the voltage 40 and the power is 10 kilowatt. So the current will be 10,000 divided by 40, that is 250 amperes here. So 250. Now you want a current of 250. See, this is a current control problem. It says we want, it's basically, it doesn't directly tell you, but it says I want to transfer 10 kilowatt at 40 volts. So that's how much current? 250. So I want to have 250 amperes current. It's a current control. Right? So current is 250. If I want to have 250 current, and here is 40, how much is the voltage here? 40 plus the voltage drop across this one. Right? Voltage drop across this one at the DC level, it will be only this one, because inductor will have no voltage drop. Right? So 40 plus 10 milliohm into 250, 42.5. So now I need to have 42.5 volt here and 40 here to transfer 10 kilowatt. So my duty cycle will be 42.5 divided by 100, which is 0.425. Okay? So the entire range of operation of the duty cycle is between 0.4 to 0.425. So you can see there is something not very nice. Right? We are only between 0.4 to 0.425 for the entire range. And that's, you see, this is in nature of power electronics. It will have this challenge. And we need to somehow fix this problem. And you will see what happens because of this problem. Okay. But before talking a little bit more about this problem, it says, how much is the peak-to-peak current ripple? We said inductor current is like this, right? Just going up, going down, going up, going down, like that, inductor current. So in the steady state, let's say 250 is the average of the current, right? The average of the current is 250. So it goes up and down. How much is this peak-to-peak ripple? So this is 250 for the average. Okay, so you need to find out, if you want to calculate this thing, you need to find out how much is this time, which we know, because we know the entire time, and we know the duty cycle, so we know how much is this time. And we know how much is the slope of this line. And then we have the equation LdI over dt is equal to VA minus VB. This is during this rising time. You remember, you see in this equation, I forgot this term. I ignored this term, Ri, because that term is small compared to this one. And this is the one that really generates these ripples. Now, in this item, we are within those short times, right? In the previous item, we are looking at DC, long time scale. Here, in this item, we are back to these ripples. Okay, so we have time, and we know this voltage is VA minus VB, and we know L, we have dt, we can find di. So di will be, or delta I will be dt into VA minus VB into L divided by L. Okay, so you calculate that, and that gives you 15.9 amperes. So you may say, why didn't I calculate that during the falling time? Well, you can do that, no problem. But if you calculate that using the same formula during the falling time, you will get 14.4. There is a difference. 15.9, 14.4. Which one is the correct one? Because in the steady state, they should be equal. If it goes up this amount, it should go down the same amount. Otherwise, it's not a steady state. It's still changing. But the reason is because we ignored this term, that term Ri. Right? So you can say this level of error, if you are okay with this level of error, 15.9, 14.4, so you can say 15 is a good average of the two. So peak to peak is 15. Okay. But if you don't like it, you need to consider this term also and solve the equation. It's a little bit of mathematics, and then find the exact value. Okay. So conclusion, 250 is the average current in the steady state at the rated operation, peak to peak 15 amperes. And so it's like 7%. 15 compared to 250 is about 7%. So 5%, 7%, 10%, even larger amount of that, depending on the application. It's normal to have peak-to-peak ripples of 10% of the rated in the current. So you may say, why don't I decrease this ripple? How can you decrease this ripple and make a very nice, smooth current? You have two ways of decreasing that. Either decrease the time or increase L. So either decrease dt or increase L. But both of them are expensive. Right. So that's why always in power electronics we have this trade-off also. How much I choose my inductor, how much I choose my switching frequency. Because larger switching frequency means more expensive devices, more power losses, switching power losses. Larger inductance again means more expensive or bigger inductor and more losses in the inductor. So if you are okay with 10%, keep it 10%. Don't try to decrease it to 2%. Keep it 10% because it's going to be costly. Okay. So that was this aspect. Assume that the converter is operating at full load. Oh, and this is a good item. We are going back to that problem that I referred to, 0.4, 0.425. You will see what is the consequence of that problem. Assume that the converter is operating at full load with a calculated D, which is 0.4, with the voltages of 100 volts and 40 volts. Now, the input voltage drops 2%, tiny amount, 2%, from 100 to 98, while the output voltage is still fixed at 40 what happens. Okay, we're going to see what happens. And remember, these voltages, VA and VB, in practice, these are coming from different sources. So maybe it's on the terminal of a battery, on a load, somewhere. So when we say 100 volts, we say rated 100 volts. It could be 98. It could be 97. It could be 103, right? But you see, if the duty cycle is at the rated is 0.425, I said 0.4. So at 0.425, now the voltage that generates is 0.425 into 98, not into 100. And that is 41.65. And if the voltage is 41.65 minus 40, that's the voltage across the resistor in the steady state, divided by the resistor, that gives you the current, 165. How much did we expect? 250. Now we get 165. Just because your input voltage changed 2 volts, 2%. Very tiny amount, but you lost 50% or 40% of your current. Okay. Now look at another scenario. Let's say this time in this scenario, the output voltage drops. Again, 2%, from 40 volts to 39.2. Okay, the input voltage does not change. So 100 volt, duty cycle, same, 0.425. Multiply that, so you get 42.5 on the diode side, terminals of the diode, minus VB. Now VB is 39.2. Divided by the resistor, 0.01, you will get 330. Yeah. So how much? 80 volt, 80 amperes, more than what you expect. So if you calculate the power, it will be 12.9, 13, almost 13 kilowatt. In the other one is 6.6. So you wanted 10 kilowatt, but it's 6.6. You wanted 10 kilowatt, but it's 13 kilowatt. So it means this basically, if you want to just apply the duty cycle and forget about VA and VB, you cannot really get what you want. This circuit, you can say this circuit is very sensitive to VA and VB. But VA and VB are not the only ones. Another thing is R. It is also sensitive to R. Let's say now our resistor is, rather than 10 milliohm, is 15 milliohm. Okay, we assumed it is 10, but it turns out to be 15. Sorry, 11. So if you do the calculation now, you have 42.5 on the diode side, 40 on the B side, divided by 0.011, 11 milliohm. That will be 227. Better than previous case, but still large. So from 250, it dropped to 227. Because only your resistor is 1 milliohm different from what you assumed. Okay. So what is the... Okay, we'll come back again to this. So we identified 3 problems: sensitivity to VA, sensitivity to VB, sensitivity to R. But we haven't given you a solution yet. I will give you a solution. But before going there, it also says what is the settling time of the response when the converter starts from 0 or when a new change is applied. If you look at the transfer function of the system, it has 1 over Ls plus R in the transfer function. And tomorrow we go into details of that. But for those of you who know transfer functions, you know a transfer function like this, time constant of this transfer function is L over R, time constant. And settling time is 4 tau, 4 or 5 tau. Some people say 4 tau, depending on how accurate you want to get there, or some people say 5 tau. So that means it takes this time for the response to reach the steady state. In this case, L is 400 microhenry, R is 10 milliohm. If you divide it, that becomes 40 milliseconds. And then 4 times or 5 times this one is 200 milliseconds. So when you start the circuit from 0, it takes 200 milliseconds for the current to rise from 0 to 250 and then stay at 250. This is the time that it takes to get there. Okay. What would you conclude from this study? Is that for power export application, it appears that the operation of the converter is much sensitive to parameter uncertainties or changes. This is what I mentioned here, but again, to repeat, because it's very important, we saw this major problem with this converter. If we cannot solve this problem, we cannot really use this converter in practice. But I'm going to give you a sensitivity analysis in this section. We do some mathematics a little bit to see really what this problem is in terms of mathematics, and then how to solve this problem. But I'm not sure how much time I have. Done? I'm sorry, I'm a little too slow, but I think at the beginning it's all right to make sure that you can catch up with me. Okay. And I think that even in my classes that I teach, I say to my students, the objective is not to finish the book or to finish something. The objective is really to learn. So just let's assume that I can only teach you half of what I'm supposed to teach. But then you learned well. So you can go and read on your own. But if I teach you everything and then you don't learn, that's worse. All right. So I do my best to cover as much as I can, but make sure also to explain well for you. Any questions about what we discussed today? Maybe a few minutes. Any particular or general question about these two classes? Do you? No, I didn't talk about demand response. No. Yeah, it's a very important topic also, yes. Yeah, I think I mentioned somewhere in my explanations, but I did not explain in the class. Yes. Demand response basically means now we shape the basically demand, you see. So we have generation and we have demand. Demand is another word for, you can say, consumption. So normally in the conventional power system, demand is completely stochastic. We don't work on the demand. Anytime you want to turn on the light, you turn on the light. Anyone you desire to turn on your AC, you turn on your AC. So that can we now put a constraint on that such that this system works better? In other words, your AC, you can only turn it on at a particular time. You can turn it off at a particular time. So you can shape your demand, or you can get the response from your demand, the response that you want. It's a very interesting research topic, very dynamic and active research topic. Is this your research topic? Okay. It's a very good topic, then very dynamic, yeah. A lot of activity is going on.
My question, actually, I'm thinking that will be covered in a subsequent lecture by you only. But my question is, in two-stage converters, when it comes to solar application, the DC-DC converter, then DC to AC converter for DC to AC, who will take care of that DC delay to maintain at certain level? Whether it's a DC-DC converter from solar side, or it's an inverter from the grid side?
In the PV application, it's the inverter, yeah.
It's the inverter who will make that DC delay.
Right. Right, because the first one takes the responsibility for controlling the PV voltage. And we said it can only control one. It cannot control more than one. If there is a scenario, and at some point we go into that, if there is a scenario that you release the first converter from controlling the PV voltage, how? Again, you will see. There are situations that you can release it and say, don't worry about that voltage. Can you control this one on the other side? And then again, you may say, okay, who is going to control the other voltage? And you will see if the whole situation is put together in a proper way, the initial voltage on the PV terminal will automatically be controlled. So there is a situation that you can release the first converter from controlling the PV voltage and assign it to control the DC link voltage. But this scenario is not very common. The common scenario is that the first converter controls the PV voltage and the inverter controls the DC link voltage. Yeah. Any other?